Okay, so this is work performed in Sheffield by Dr. Rahi Rabari. Unfortunately, he's unable to travel because of some visa issues that if he leaves the UK, he may not be able to get back in. So he's staying home. This is looking at transition zones and thinking about, is there a way we can do them better for low-density lines? And the original idea came from people in TCDD. During setting up the project, they had an idea about varying the mass of sleepers. And was there a way that by varying the mass of sleepers on the approach to a transition zone, you could reduce dynamic loads in the same way that we currently do with earthworks, varying the stiffness of the earthwork support. So to carry out this work, we took a finite element modelling route, and originally that work was carried out with the rather complex finite element model on the left-hand side there, fully 3D model, that was unfortunately rather heavy and rather slow to run. So we got some useful things out of that, but we realised partway through that we needed to go faster, and so we moved to a 2D finite element model, which is the one on the right there, and that enabled us to simulate not just one wheel passing by, but a whole train. So in this case, you can see the small circles are running along there. We've got enough for 40 wheels on a 10-coach train. And what we're trying to simulate, or what we are simulating, is approaching a bridge structure and the changing ground stiffness as you approach a bridge structure. So this is conventionally an area where you're going to get a lot of dynamic load as you move from quite flexible ground onto a quite rigid bridge structure. And typically it's somewhere that a lot of earthworks would be done to try and reduce the stiffness variation. And it's an area where there's a lot of tamping maintenance required to try and correct track geometries. So I believe that started the video, and we should see the wheels moving along. And this is displacement in the soil as the wheels are moving across this region. And I think we've got a whole train worth of wheels to go past. So this was the development state of the model, probably looking back to around the midterm conference. And at that stage, we got a model that ran, but we needed to conduct verification of it and validation of it. Now, within the NeTIRail project, we did not have the budget, and we didn't plan to construct a new transition zone and test this. But what we could do is draw on work from another EU project. So this is work that had already taken place in Portugal, in which they had taken a bridge structure that was under construction and modelled very carefully the transition zone approaching that bridge. So here you've got it in part A of that slide during construction, before the actual track has been laid next to the bridge, and in part B after they've completed the embankment and also the track on top. So the monitoring they did there we could use to verify what we were doing in our models. So what they've got there is the transition zone from if we look on the top, the bridge structure is on the right, and approaching that is a graduated construction of embankment to give a variation of stiffness as you approach this bridge. From the natural earth embankment through the unbound granular material to bound granular material with cement, and then onto the rigid structure. So this is aiming to give a transition of stiffness along that structure. And with that, they were able to monitor displacement under the train load. So the train load is shown on the bottom slide there. It's a multiple unit train, so we've got reasonably even distribution of load through the train. It's not a locomotive, it's an auto-driven train. And the ballast construction was also very well documented. So the different layers of the ballast and the subgrade underneath that. So we have everything needed there to put into the model and verify our model, and then begin changing our model to this new idea of varying sleeper mass to understand whether that could successfully replicate what a proper transition zone does. So here we've got the FE model you saw previously with the wheels rolling along the top, and now underneath it we've got the transition zone, replicating the one that was built in Portugal. And we've got a version at the bottom there without any substructure. This is a region for stability where we can introduce the wheels into the model. They begin rolling along the track and reach stability. So when they enter the transition zone region, they're in a uniform state. So we actually understand that the response is due to the transition zone, not the wheels entering the model. And this was the data from the Portugal transition zone, and this was modelling that they undertook. So we had access to that data. So this was the start of our work, in which they got the blue being their experimental measurements and the red being the simulation measurements from their work. And they gave vertical displacement along the track, spelling mistake there, two distances back from the bridge abutment, so about 15 metres back and 41 metres back. And those gave us a reference point with which to compare our model. So track displacement, you can see the pattern with which two wheels on a bogie pass over a location, you get the double dip, and then a space. The next one, there's two bogies from two vehicles, so you get 4 dips in the motion. And the behaviour is slightly different at 14 metres from 41 metres back from the bridge abutment. So that was the data we had to compare with. But we could then do the modelling and start to understand whether we could replicate what they were finding over in Portugal. So here's the output from the models that we developed in Sheffield. And this one was just saying, let's model it with a uniform embankment and model it with a transition zone to understand what the conventional transition zone is doing for us. So here we've got two lines. The blue one, no transition zone construction, just a uniform embankment. And the red one, a transition zone constructed as they did in Turkey. The first thing you might think is, these curves all look about the same. Well, at 41 metres back from the bridge, they should look the same, because by that stage you're off the transition zone, you're on the embankment. And so the construction with and without the transition zone in place should look the same, and indeed it does. Closer to the bridge, which is the top graph there, they also look the same until you look in detail. If you look at the blue one with no transition zone construction, you'll notice the bottom peaks in this, the lowest displacement, is larger for the blue case with no transition zone construction. So we're showing that the transition zone construction has reduced displacement on the approach to this bridge caused by the wheels passing over. So we're verifying that the conventional transition zone construction is doing what it's supposed to do. Is there another way of doing it then? Can we achieve the same kind of thing without constructing a transition zone? Well, here's several attempts at doing so, and what we've done here is, on the left-hand side, it's again 14.7 metres back from the bridge abutment. On the right-hand side is 41 metres back from the bridge abutment. And in each case, we've got 3 different masses of sleepers. So we've taken conventional mass of sleeper, which is times 1, indicated there. We've halved the mass, we've doubled the mass. So this is something that you could do on approach to a transition zone without all that earthwork. And there's an awful lot of data on this slide, but we've done that with varying sleeper mass on top of the transition zone, varying sleeper mass on 2 different cases then. And really the bottom line is where we're interested, which is the one where we're not having any geotechnical construction. It's just a normal embankment without all the complex transition zone. And it's a little bit small on the screen there, but what you find is that the peak deflection is reduced quite considerably if you use the double mass sleepers, to about the same extent that it is by actually constructing a proper transition zone. So in terms of installing this, you would have a much, much cheaper installation to just make a normal embankment and use the double mass sleepers. And that looks like a very good way of making a low-cost transition zone and reducing displacement without all that construction. The data is quite hard to see in that graph. There's some histograms there which try to pull it out. There's an awful lot of data in this presentation, I'm afraid. What we're looking at is the bottom 2 graphs, which are again the 14 metres back from the transition, from the bridge abutment, and the 41 metres back from the bridge abutment. And you'll notice that around 0, there is a lot of high frequency of the data. Whereas for the other cases, there's quite a lot going into the positive territory. And this is showing the reduction in displacement we've achieved by going for the high mass sweepers, which are in the bottom two figures, double mass sweepers. We're able to reduce the amount of deformation that was happening, the displacement of the track. I think that's the last slide on this, so it's a very quick look through that. But the overall story is we are showing through the modelling that the double mass sleepers have the ability to reduce deformation approaching the bridge in the same way that all the geotechnical construction does. I think the next stage, this is output of modelling, next stage with the budget we need is to go and build one and actually try it and monitor it. So that'll be the next sort of exciting project to do, I think. I think that's the end of the presentation right here.
Thank you very much.